Welcome to P. Clark Calc, Practical Calculus for the Busy Math Student. And in this video, we're going to take a look at some cases where you can find the value of a definite integral geometrically. And it's a useful tool now and again, so let's take a look at how that works. Here we're taking a little different look at the definite integral. We've already seen how to use the fundamental theorem of calculus to find the area under a curve. Huge definition. It states that the area under a curve is represented by the definite integral of f of x dx from a to b, and you can find that value by taking the antiderivative of the upper bound b minus the antiderivative of the lower bound a. So we could use that pretty simply here on this example, the integral of x dx from 0 to 4. But there's another option that's out there, and that is to actually find the value of a definite integral geometrically. If you look at our definition of fundamental theorem on the right, we probably would not have that option here because it's not a geometric shape. But sometimes you get lucky, and when you take a look at the region that the definite integral is describing, you can actually calculate the area without having to do an antiderivative. So let's do that here and just make sure that's all working for us. So we're going to need the graph of y equals x from 0 to 4, so let's get that in here. So if we understand what this integral is describing, the area under the curve y equals x and above the x-axis as x goes from 0 to 4. So if we would go ahead and sketch the actual region that's being described, we're looking at this, which if you recall from your geometry days is a right triangle, so we could actually find that area using 1/2 base times height. So in this case, the base is 4. And the height is also 4. And we very quickly come up with the value for that definite integral as 8, and we did it just using geometry. Now, in this particular case, we could go ahead and have used the fundamental theorem. It always works if you can find the antiderivative. So let's just check our answer doing that. Pretty simple case. We have 1/2 x squared. Remember your notation here, the vertical bar means we're evaluating the antiderivative from 0 to 4. So that gives us 1/2. A lot of times when you have a constant multiple, it's nice to kind of pull that out of the evaluation. It's going to be a common factor if you leave it in there anyway. So we have 1/2 times 4 squared minus 0 squared, which obviously gives us the same value, and why wouldn't it? But it's just one nice example of a case where you could, if you recognize that as a right triangle, go ahead and do that definite integral without calculating the antiderivative. And that's a little bit more useful when we take a look at this next example. So here we're looking at the definite integral of the square root of 9 minus x squared from -3 to 3. And if you try to use the fundamental theorem there, we get a pretty serious question, which is what in the world is this capital F of x? What is the antiderivative of that function? And at this point in your calculus life, the answer is it's something very, very difficult and nothing anyone's going to expect you to actually figure out at this point in time. It's a very difficult integral. You wouldn't think it just by looking at it, but just kind of trust me on that for the moment. However, we get lucky here because we don't have to figure out the antiderivative if we remember what this graph looks like. It turns out that the graph of this function is a semicircle. The square root of 9 minus x squared is the upper half of the equation x squared plus y squared equals 9, which is a circle centered at the origin with a radius of 3. So that's what we're looking at here. And so by understanding the area of a circle formula from geometry, so the area of a full circle is pi r squared. So that means that the area here on our semicircle is 1/2 pi r squared. And so our radius is 3 by looking at our graph, and so we can just go ahead then and evaluate our integral this way, as long as we recognize the geometry going on here and the fact that this is a semicircle, and you get a much simpler conclusion here than if you would go ahead and do that antiderivative, which actually for right now for most of you is well above your pay grade, so some other time, but you just have to trust me for the moment. Very difficult integral, so even if you do know the antiderivative, the fundamental theorem is not the best way to go here. Is to use the geometry and understanding the direct connection between what the definite integral is saying and what it represents graphically. And that's what allows us to do that in certain cases. Now, obviously, in most cases where calculus is helpful, it's not a geometric figure with a formula, so then we do have to use the fundamental theorem or some other strategy at that point in time. If you'd like to learn more about definite integrals or calculus in general, you can find more on my textbooks, which are available for a nice price on Amazon. Until next time, I'm P. Clark.